Hello again, everybody, and welcome to another Geo-Institute live stream. Today is special for a host of reasons. Number one, it's our 50th live stream of the year. We've never made it to that before, so that's a ton. And thanks to all the presenters and all our hosts and moderators and Aurora Flieger, Amber Davis, and Christina Scott, and all the people around GI that make this happen. It's crazy that we've done so many this year. So woo to us. My name is Brad Keeler. I'm the director of the Geo-Institute, and welcome again to our first live stream, our first lunch and learn for this year's web conferences. If you don't know anything about the web conferences, maybe we'll talk about that in a minute. The first thing I'll say is if you don't know anything about the Geo-Institute, after you watch this today, head over to geoinstitute.org, and there you can find out all kinds of amazing things about us, including that we are a technical society with about 12,000 members, most of whom are geotechnical engineers and or geologists, and that we are part of the American Society of Civil Engineers. If you like what you see today, and you're going to, we saw part of the presentation already. I know it's good. You're going to like it. You should click like, subscribe, and get notifications, and we will let you know every time we post something to the YouTube channel. Now, back to that web conference. Every year, we do this in December. 10 of our technical committees take a turn, put together amazing sessions. You can register for those a la carte. You can register for the whole thing. There's information on that at the website at geoinstitute.org. Head over there and check it out. We have 5 sessions remaining for the week, including one this afternoon. You can still register for those and take part and get your PDHs at the end of the year. It will be an amazing experience. I personally guarantee it. The other thing that you should do, because we are drawing close to the end of 2025, is perhaps make your contribution to Geo-Institute student programs. Right now, we're trying to endow student programs. Jean-Louis and Janet Briot gave us a $500,000 donation last year, and we're trying to match that to endow our programs. Bob Bacchus from GeoSyntech came through with a $25,000 contribution earlier this month, and we are trying to match 10K of that by the end of the year. So if you head over again to the website, click on Student Participation Fund, Student Program Contribution. It says something like that at the top of the page. We have amazing thank you gifts like this Ralph Peck bobblehead. It could be yours. Now, today's presentation, Keller is our gold sponsor, as they are almost every year for the web conferences, and we are thrilled to have them back at that role for another year. That means they do a lunch and learn. All the past ones are up on the Geo-Institute YouTube channel. You can check those out. We're happy to have Juan Salinas here with us this year from the Shenandoah Valley to tell us ground improvement successes and pitfalls. Here to tell you what you're gonna hear is GI superstar, local involvement committee member Keith Merle from Morris Shea in the Philadelphia area. Keith, time for you to run the show.
All right, thank you, Brad. So I'm happy to introduce Juan today, senior engineer with Keller. He's been beating around in the industry for about 12 years now, doing consulting and geotechnical design. Another one of those Virginia Tech grads that are everywhere. Don't see as many Drexel guys out there, but he's licensed in almost a dozen states, and obviously his expertise is in geotechnical evaluation, foundation support, earth retention structures, and risk mitigation. He works on a bunch of projects around the U.S. and involves residential, commercial, industrial, and a bunch of mission critical developments. So right now, Keller's got him specializing in design and implementation of ground improvement systems, and he's serving as the engineer of record on projects throughout the South Central U.S. and is part of Keller's largest business unit in that role. So without further ado, I'd like to introduce Juan. And as questions do come up, I think for now, we are going to just hold those to the end. So please post your questions. I'll get them all teed up for the end of the presentation here. I will say if something seems like it fits good, I might interrupt you a little bit, Juan, but sure. Take it away, sir.
All righty. Thanks, Keith, for that introduction. Really appreciate it. And really appreciate big thanks to Geo-Institute and ASCE for organizing this webinar series, for allowing me to be a part of it, Keller for sponsoring this event, and letting me share some of the stuff that I've learned over my last couple of years here as a part of our ground improvement team. At Keller, I get to work on a ton of geologic settings, and I partner with professionals, engineers, consultants, and contractors throughout, a pretty large area, about 30 states. And I've got, some things I want to share with you guys. My presentation really isn't necessarily intended to be groundbreaking for most of you, but hopefully you'll see at least one thing in here that's useful to you in some way, shape, or form. So, quick agenda. I'm going to go over an introduction to Keller, what we do, what our capabilities are. Then I'm going to talk ground improvement overview about the two techniques that we're really focused on today. Probably should have named it those two techniques instead of ground improvement, because ground improvement entails a lot of things. But then we'll get into some subsurface exploration and testing, discuss structure and design. I've got a slide on that has a dense amount of information. Going to hit some points on construction quality control. And then I've got 3 studies that I think are going to tie it all together. So Keller, if you're not familiar, it's the world's largest geotechnical specialty contractor, and we leverage our global strength with local expertise to deliver optimized geotechnical solutions with a high emphasis on sustainability, high performance, and safety. Our parent company is based in the UK. We are publicly traded on the London Stock Exchange. I'll point out that ever since I joined Keller, things have gone way up, so doing pretty good there. I think this year we're on track to do something like 4 billion in revenue, I believe, somewhere in that neighborhood. So doing great, and I think we're poised to have a really strong start to 2026 as well. Excited to be a part of this team. Keller does everything, right? We do ground improvement, defoundations, earth retention, groundwater control. These are just some of the things that we do. Again, the focus of this presentation is on 2 of our products that I get to design kind of day in and day out: rigid inclusions and aggregate piers. So ground improvement refers broadly to just techniques that, increase your soil bearing capacity and reduce your settlement and let you design your building as if it were on shallow spread footings, right? So it kind of simplifies the structural design side of things, saves you money because you get smaller footings. And these are just some of the typical characteristics of the 2 products that are the focus of today's presentation. Hopefully most of you are familiar with at least one of these products. They're great for supporting tanks, buildings less than about 12 stories, although Keller has gone higher than that. Parking garages, embankments, MSE walls. They're very versatile products installable in a wide range of geologic settings. I think the most important thing to understand about the mechanisms by which these 2 techniques improve the ground are that aggregate piers, they share the load with the ground, and they work with the surrounding soil matrix to improve the engineering parameters. But they rely heavily on that soil to offer some pushback there and the confinement needed to develop that stiffness as you install them with tamping or vibratory energy. And this makes them really not suitable for very soft soils or organic soils. Rigid inclusion, on the other hand, are much stiffer and transfer the soil through the soil layers. There's still some load sharing there, but it's less than due to the higher stiffness. And they're kind of like CFAs, right? Without reinforcement, they're much more like piles in many ways. They are piles, and they're not connected structurally to the building though. So you need a load transfer platform, and you need a finite element analysis to kind of understand that interaction between the piles, the LTP, and your rigid inclusions. So there's structural considerations to be mindful there. But I'll note that the LTP doesn't necessarily have to be any one thing. It really just refers to the material that occupies the space between the top of your RI and the bottom of your footing, and it can be relatively thin, it can be thick, it can have grid reinforcement, it can be made up of different material types. So it really depends on the application. And one of the risks, I guess, would be that it's because it doesn't have reinforcement the majority of the time, it has pretty low lateral capacity. It's not ideal in seismic settings, but it can still be installed there if you reinforce it. Into some stuff, this is the section that hopefully most of you guys are pretty well versed and familiar. But the reason I've included it is just because, again, I get to see a lot of different reports through different areas of the country, and they're not all created equal, right? So I think first and foremost, we want to understand and identify the geohazards. We want to carefully review the geology information. It's critical that we understand where we are installing ground improvement, and the more data we get, the less risk, right? This is something I'm sure we're all on board with. We really need to think about the number of tests and the depth of testing with respect to the structure footprint and the depth of stress influence, right? And I mentioned this because I've seen reports where we're doing 15-foot or 20-foot borings for maybe a 5 or 6 story structure, and then we're terminating them in 2 blow silts, right? We don't want to be doing that. That's not particularly helpful. We should consider training our drilling teams, our field engineers, to maybe dynamically adjust our explorations to gather the appropriate amount of information so that we have success with these projects. And then soil variability, right? Sometimes your footprint is rather large, and I see project reports with only 2 or 3 borings in that building. 2 of the borings maybe are showing pretty consistent conditions, and then you have a third that's showing a dramatically different profile. And I think that project probably could have benefited from, some additional testing in that transition zone to really understand what is happening on that particular project. SPTs are great, right? We do them on almost every project, but CPTs, DMTs, and PMTs are oftentimes a game changer especially for sites with cohesive soils, right? I have this image here from that I've pulled from a incredible paper by Roger. I don't want to mispronounce his last name, Fail-Mesker. Hopefully I got that right. He wrote this in 2021 called The Financial Failure, The High Cost of Not Knowing. It's a phenomenal work. I don't want to do a disservice to it by summarizing it too quickly. I highly encourage you to check it out. I think we're going to make the link available to this paper because I think it's one of the most important contributions to our field. So please check that out. But the idea that I want to borrow from it is really just that as you decrease, as you lower your uncertainty, right, you lower the probability of financial failure. And we'll touch more on this in one of the case studies. This slide just has a couple of more specific types of testing that we would want to do for certain job sites, right? So things like rock quarrying, geophysical studies, air track testing, enkarstic conditions and limestone, having really good photos, clear pictures, detailed descriptions. These are paramount to having a successful outcome and an optimized design. We'll see in one of the case studies why I mentioned these things. And things like post-fill placement testing and post-blast testing can also make a substantial difference. Lab testing, our focus here should be on understanding soil behavior and composition, right? Atterberg limits, moisture contents, grade size are relatively inexpensive ways to gather some pretty good data, right? To really supplement that information you're gathering from your SPTs. But you'd be surprised how many reports I've seen come across my desk without a single lab test of any kind. I'm talking not a single moisture content. And it's kind of shocking because we should all be aware, hopefully, that not all clays, silts, and sands are created equal, right? Even those with equal N value. And that could be a result of their composition, but also things like their stress history. And testing really needs to be performed at critical layers, which are often found deeper. I have found in my practice, oftentimes, for whatever reason, testing seems to be very concentrated in the upper 10 feet of soil. But sometimes the most important layers to analyze are kind of deeper down. So if you find some weaker layers deeper down, those are good spots to check them. Things like consolidation tests, direct shear, triaxial for ground improvement, these can make or break a design, right? And obviously organics. What I see a lot is qualitative descriptions of organic content. So things like, this boring has little organics or some organics or trace organics. And what we would love to see is things like a more quantitative approach, right? Because generally speaking, once you cross about, somewhere around 5% organic content, you start to wonder if aggregate piers are even viable for this project. So I would encourage you guys to, do some loss on ignition testing and keep that in mind that some of the qualitative descriptions may not be as helpful. I have one slide on structure and design that kind of packs a lot of information. With our focus here being on the soil structure interaction and the requirements, right? We need to figure out what are the real settlement tolerances and what are the real loads, right? I think since ground improvement design really works to control settlement to within that tolerance, we need to know the forces that are going to induce that settlement, right? And in this case, is going to be your dead load and your live load, right? That's what's used to predict settlement. Things like wind loading, for example, are accounted for in your bearing capacity, but they're not going to induce that creep and that settlement over time, right? So we need to know the dead and live loading at every footing location if we're going to make settlement predictions, right? You can see here on the right this bearing pressure diagram for the large mat. If you were to put full 6,000 PSF on that thing, that's gonna, you're gonna predict a whole heck of a lot of settlement that is not realistic, right? In reality, the pressure distributions that you see there never exceed 4,900 PSF, and on the right side are actually significantly lower, right? So your average total is a lot less, and you can really not just optimize the design for cost, but also for accuracy, right? And that's important to do. Same thing happens for retaining walls, right? You need to understand the heel and toe pressures and how those are going to influence the ground. The other really important thing is to understand overlapping stresses, right? There was a project that we were looking at some time ago with very large tanks, 100-something diameter tanks, all kind of situated in a line and spaced about 15-foot apart, edge to edge, something like that. If you plug that into Settle 3D to understand what was happening, you'll notice that the center tank settles substantially more than the other two, and that the other two on either side will have some tilting action happening, right? You'll have more settlement on the side that's adjacent to the center tank. And that's because of these stress bulb influences. We need to understand that. We need to figure out the impact of that on anticipated settlement. So that's something to think about. And then with respect to uplift load demand, we don't see these very often for ground improvement. In the limited cases that we have seen them, it's worth initiating a conversation with the structural engineer again to really understand what the requirement there is, and if that uplift demand is real, or is it actually a true net uplift demand. We should at least ask the questions. Couple slides on construction and quality control. I think our focus here needs to be on understanding the true site conditions when we go to installation and keeping communication between all parties involved, right? So I think a good starting point is your working pad, right? This has implications even at the design level, and the cost implications. So is it one elevation? Is it multiple? Is it sloping? What do your transitions look like, right? This will determine whether or not our equipment can navigate it safely and efficiently, right? So this also has implications for your cost and by delaying schedules if it's messy, and we may even shut down if it's too unsafe for our equipment to operate, right? So we need to be keeping it dry and consider using soil cement if you're expecting a lot of rain, things like that. The other big thing is, we do a lot of work in data centers, and utility coordination is paramount. Having meetings, and the earlier that we start communication about this subject, the better, right? We have a lot more options. We can, with piers, utilities, and footings, they can be relocated, resized, eliminated, raised, lowered. We can also the construction sequence, install them first or redesign them, use alternate materials to limit that dig zone that you see. It's quite it's quite substantial, right? This is a little bit different again because these aggregate piers are going to rely on the surrounding soil for that confinement. We need to limit how excavations are performed in the vicinity of those, which is a little bit different than something like a deep foundation system, right? The other thing is element installation and tracking, right? So your installation length is equal to your design plus your sacrificial length, and we need to track that carefully. We need to understand, again, with respect to your working platform, what is that sacrificial portion of the pier that gets dug out as you excavate for your footings matters, right? We need to account for that and track it well in projects, especially where you have shallow rock. That needs to be understood because your design length might be fully compliant with the design intent, even if the pier terminates short of the anticipated elevation, right? We see this a lot in in Northern Virginia projects where our design will specifically state that we've accounted for conditions where, where our piers are going to be slightly shorter than intended. But oftentimes we find that these get flagged as non-compliant by either, third-party reviewers or site inspectors when they made. So I just encourage everyone to make sure you read through the entire design documents to understand what these specific requirements are there. And then having redundancy really helps with tracking, because we've had cases where our tracking documents will show something different than what the inspectors have on their notes. So redundancy can help alleviate some of that friction. One of the most important things, and again, this will be touched on in one of the case studies, is footing subgrid preparation, right? Probing it for stiffness, visually inspecting it, making sure it's dry and well compacted, and then protecting the excavation if you're going to leave it open overnight with a mud mat. Just following the notes on the design and having clear high resolution photos and field reporting. Again, because the piers work and rely on the surrounding soils, it's not enough to just have them, right? That soil matrix could become compromised even if the piers are there, right? So it's important that we take a look at what the footing subgrid looks like when we go to pour the footings. So now we get into the case studies. The first one is an elevated water tank project here in Virginia. This is in Piedmont geology, kind of along the fall line, which is the transition between Piedmont and coastal plain soils. So, your residual versus your coastal deposits. On this project, you have residual sandy silts over partially weathered rock. You'll see a profile on the next slide. And we're supporting a 1 million gallon elevated water tank designed for 5,000 PSF. This had typical settlement criteria of 1 inch total and 1/2 inch differential, but that should catch your attention for, and we'll see why in a minute here. This is kind of what the layout looks like. You have a center pier with 24 by 24 footing, and then all the perimeter footings are about 14 by 14. We completed aggregate piers on this one in January 2024. And in April 2025, the tank is filled 60% full, and the center pier has been measured to have settled about 2.5 inches, although the perimeter footings had only settled about 0.7 inches, give or take. So this is the soil profile. Here's about where your bottom footing is. Nothing particularly concerning if you just take a glance through that. The end values are not that low. These are, 30 to 40% sand, silts. And the geotech, analyzed, made some settlement predictions of totally unimproved conditions, assuming about 1,000 kips. This is higher than the actual loads. I think the actual loads were somewhere in the neighborhood of 900 kips for the perimeter footings and 2,800 kips for the center footing, with settlement predictions in the neighborhood of 1.4 to 1.8 inches, which was pretty congruent with our initial analysis as well. And we also performed a modulus test for the project that showed less than 1/2 inch of deflection at 150% of the load. The perimeter footings settling, 0.7 inches at about 60% of the load was almost perfectly in line with our expectations. So we weren't sure what was happening here. So here's a photo of the subgrade before they poured the footing. It's just the only photo available, but to me, it doesn't look great at a glance. I think it appears that the photo's kind of blurry and grainy and hard to see. The lighting's not great, but it looks a little bit wet. Doesn't look exceptionally dry or flat. And the silts in this area, like most silts, are extremely moisture sensitive, right? They lose a lot of their strength when exposed to water. So we reviewed their records from the inspectors, and there were some missing reports and some errors that made it unclear exactly what happened, but they suggested that the excavation may have been left overnight. Historic weather data review didn't suggest that a rain event took place necessarily, but it was hard to tell. So we went and performed some dilatometer testing on either side as close as we could get to the footing, and these are the results, right? So we're seeing very soft, very low constraint modulus values right at your footing bearing elevation. And that, to me, my interpretation of that is the subgrade was somehow compromised, right? Water got into that subgrade at some point somehow, and really softened those soils. So some important lessons learned there, right? Actual settlement tolerances, total and differential, were somewhere in the neighborhood of 3 to 4 times higher than we were initially told, right? We found this out over the course of figuring out what is the risk. They ended up having to drain the tank, change the piping connection, jack it up, and then reinstall it. And ultimately, I think all told, the tank ended up settling. The center pier settled something in the neighborhood of about 3 inches, with the perimeter footing settling about the 1 inch we predicted. So a total of differential of about 2 inches, and ultimately it was fine with that. So this is what I envisioned the structural engineer might have looked like after he told us that settlement was only 1 inch, or it could only be 1 inch. Obviously, footing subgrade preparation, inspection, and protection are critical to ground improvement design, right? So really want to drive that point home. And field documentation needs to be clear with high quality photos and checked for accuracy and continuity. The second case study is the Knoxville building in Tennessee. This is in limestone, karst geology. Knoxville is known for having some pretty variable conditions out there. On this particular project, we have some very soft alluvial clays over rock. It's a 3 to 4 story mixed use building on shallow spread footings, designed size for 9,000 PSF. In reality, the actual loads, the footings don't need anywhere near that capacity for the most part. There is a large retaining wall kind of running along the back of the building here. And that 9,000 really kind of is concentrated to only one small area of the retaining wall, where the property boundary kind of prevents them from extending their footing out further and reducing that 9,000. But yeah, most of the building doesn't actually need anywhere near that much, right? Your column loads are only in the neighborhood of about 130 kips, and the typical settlement criteria: 1 inch total, half-inch differential. So we installed some grouted piers to refusal, anticipating that to be somewhere in the 15 to 25 foot below surface. But it was pretty clear that we had some subsurface exploration deficiencies, right? In this karst geology, we had no rock cores, no air track, no geophysical study, right? We just had basically SPTs, hit refusal, and then just stopped, and that's it, right? So half the borings were actually off the building padding, sort of concentrated to one side of the building. So really, when they figured out that where the final building location was, we probably should have had a couple more borings on the other side to have a balanced understanding of what was happening on this building. And we also had no CPTs, DMTs, or PMTs, or consolidation testing of the clays. All we kind of knew was that the moisture contents were pretty high, so we really did not expect the clays to contribute much at all. These had to be designed again as almost entirely just pure end bearing elements, assuming that the limestone beneath was pretty sound rock, which it wasn't. So we had some issues with installation and performance. Some of our guarded elements started kind of plunging into the ground after installation. We could not achieve refusal at some location because, I think as far as 30 foot down, due to our equipment limitations. So the rock basically was deeper than we anticipated that it would be from the available geotechnical information. And our first loads test underperformed. So I wasn't actually not initially involved with this project. It sort of landed on my plate a little bit later on. And when we started encountering these issues, I sort of knew exactly what to do. But in a much more real sense, I had no idea what to do. So got with the engineering team, and we came up with a whole bunch of remediation efforts and solutions, right? So we directed some rock coring. Obviously, we needed to understand what kind of rock we were looking at on this karst site. And it showed that we had voids and extremely variable rock quality, right? So we started doing some proof testing of the production elements and got a lower capacity. We were able to make certain areas that were much more lightly loaded portions of the building work with a lower capacity. We performed additional load tests, one with grouting the voids below the piers and one without. And unfortunately, both tests also underperformed. So we reduced capacity for that as well. The reaction anchors for those tests also continued to confirm that the rock was extremely variable on this project. And at locations with higher loads, we just had to redesign it completely and come up with an alternate solution. and we had to grout the majority of the larger retaining wall area. It was a kind of the remediation plan. You can't really tell what's going on here, and that was sort of the point here. It's just that it's very, very complicated. Every single element had to basically be analyzed individually. Lots of good lessons on this one, right? Proactive controlled investment data costs are in almost all cases less expensive than reactive surprise remediation costs, right? I think this is a very powerful image that kind of captures that sentiment, right? You kind of know what your geotechnical investment, it's a defined cost, you know what it's going to be, and you have no idea what your subsurface surprise cost could be. It's uncapped liability, right? The other thing on this one that was very interesting was that structural engineers really are very conservative oftentimes, right? So throughout the course of this project, the actual loading provided by the structural engineer changed, I want to say something like 4 or 5 times. By the end, with the final as-built, some of the footings, the loads provided from Rev 0 to the final as-built was something like 50% lower than what we were initially told. So yeah, I don't have an exact number for the total losses incurred on the project as a result of the lack of information and the structural changes, but I know it's somewhere in the neighborhood of double the cost of the original price, not accounting for scheduling delays. And then obviously karst is just one of the most challenging geohazards that we navigate. And finally, we have data center Virginia. There's very many of them, so hopefully you can't guess which one. This is in Piedmont diabase. Diabase is extremely hard rock. On this particular pad, we have a combination of pretty substantial cut areas and fill areas, something like 30 feet, give or take, from one side of the building to the other. This profile doesn't exactly show how extensive the cuts and fills are because it's kind of running through only a diagonal portion of the building. But from here to here, it was pretty substantial. And we have boulders and blasted rock. It's a pretty heavy 3-story data center size for 8,000 PSF, with the typical column being a 19 by 19 or 20 by 20 footing, and having column loads of about 2,100 kips. Again, typical settlement criteria of 1 inch and ½ inch total. We used a combination of RIs and APs to install to refusal. And the cool thing is that this project was actually originally priced with drilled shafts at 3 times the cost, and then micropiles at something like 2.5 times the cost, and finally built on VPs or APs and RIs. Lots of challenges and solutions, right? Boulders, we had to do a lot of air track testing. I think we air track tested every single pier location to figure out, whether we were going to be end bearing on something good or a boulder that needed to be removed, and then we reinstalled piers. We had a micropile contingency for certain conditions, which luckily was not needed. We had utility conflicts, right? And almost all data centers have tons and tons of utilities coming in and out of the conduits. But we have options, right? Again, because of the coordination efforts, we could use different material types to reduce the zones of influence. We can make construction sequence adjustments, so install them beforehand, so they don't need to be dug out after we installed piers. We can move some piers around or resize some of the footings, things like that. So we assisted with BIM model coordination, and we had many meetings about it. Over blasted rock, we did some post-blast warnings, and we required deeper excavation. I think the number I was given was something like 30 to 50% change order because of how much more we had to install. They overblasted the rock way beyond what they were supposed to, or what they even really needed to. And then still we had shallow rock refusal in many cases. So we really needed detailed tracking, right? Some of these larger footings had piers that were installed to length, some that could not be, and we had to make sense of that. So we did a case-by-case evaluation of every footing, what needed to happen there. And that also required quite a few meetings. So one of the other challenges is that we had too many meetings, right? And some of these calls, we had 40, 50 people for some reason. I have no idea why. So I think we need tighter focus on the meeting, and we need less people in the meetings, and just less meetings overall. But on this one, you get a meeting, I get a meeting, everybody gets a meeting, right? Lessons learned. As you can probably tell, hopefully you can still tell, this is an AI image, right? So this is not the site, and nobody got what was hurt. APs can be a great value engineering solution in good soil conditions, even for heavier buildings, right? So above the diabase rock, we had very good residual soils, and it made APs possible. Saved a lot of money. Post-blast borings really need to be performed to determine the extent of possible overblasting on certain projects. I think that was kind of an eye-opening lesson for us. I think sometimes maybe we assume that the blasting is a very precise operation, and it might not be, not necessarily. And the utility coordination efforts are valuable, but they need to be performed efficiently. That's it. 30 minutes on the dot. Almost. Ready for any questions?
Juan, really appreciate that. There's a couple times that having been in this industry for a while that I definitely smiled at some of the lessons learned and so forth. So let's jump right in. I got a couple I want to ask you. So the first thing I'm going to say is, of those, we'll call them advanced testings, I'll do that sort of in air quotes, the CPTs, DMTs, PMTs, if you had to pick one, what is the one version of these sort of advanced tests that give you the most return or the best information for your design?
I think based on my experience, it would probably be the dilatometer DMT testing. That's been, I think it's the most direct measurement of compressibility, which is what we really care about the most. CPTs are probably a close second, just based on my experience. But I'm a big advocate for using DMTs wherever possible.
Excellent. So DMTs is number one on the list. Any of our geotech
yes.
friends listening? Let's remember that for Christmas gifts. So the next one, and I know this from experience, but I wanted to ask your opinion. How important is it to get the actual loading for the design of ground improvement, versus a bearing capacity or some back calculated loads from an old pile plan that you're trying to value engineer?
In my opinion, it's absolutely critical for the overwhelming majority of projects. Although, again, it's gonna, the answer will always be kind of, it depends. On the right project, it'll make a world of difference. And in certain conditions, if you have ideal soil profiles, if you have really shallow rock, which we encounter often, for certain ground improvement projects, it might have almost no impact on your scope. And yet on other projects, it might double or triple your scope, right? It really could be somewhere in between as well. So, I mean, in my mind, there's no reason not to push for actual loading. I think again, the only way to certify even things like differential settlement only makes sense if you have individual column loads, because otherwise, if you're just applying one load, how are you actually gauging the risk of differential? So yeah, that's my answer.
Do you see a significant change to that answer, aggregate piers versus rigid inclusions?
No, I think the answer is probably about the same. It really it depends a lot on the geology and the soil profile that you're working in. I think it can certainly be the case that I guess for rigid inclusions more so, you probably need the loading even more than you do for aggregate piers. But yeah, I just, in either case, the conversations need to be initiated for sure.
Excellent. So, have you ever thought about using high-strength geotextiles to create a working platform instead of the time-consuming use of soil cement and those types of solutions?
I think I've only seen one project where that was considered. I assume it's because maybe the equipment that we use isn't necessarily large enough in most cases to warrant something like that. I don't actually know, because I don't have enough familiarity with the cost side of things at that particular point. But I mean, it's definitely worth looking at, right? Anything that stabilizes the working pad is worth exploring for sure.
Very good. In case study one, was there any DMT testing advanced within the take footprint to show the inadequate subgrade preparation? Were you guys able to kind of get back to that at all?
Case study 1, you said.
That's the tank.
Yeah. So that's what we did. We did 2 dilatometer tests on either side of the as close as we could get to the footing that was experiencing excessive settlement. Yeah, and these are the results. This M value here is constraint modulus in KSF. So you can see there, those are the results of our forensic evaluation.
And in that analysis, you had mentioned that significantly higher, center pier settlement, and do you attribute that primarily to the compromised subgrade from the open excavation, or do you think there was some stress overlap that impacted that as well?
We went, I had a Settle 3D model to see if that was going to be a significant contributing factor. And it didn't look like it was going to be nearly enough settlement to account for it, right? So our analysis suggested that somewhere on the order of about 0.2 of an inch was coming from that overlapping stress, caused by the perimeter footings on the central pier. So the best explanation that I could come up with, based on everything that we saw for this particular one, was that the majority of that excessive settlement was happening in just a couple feet of compromised subgrade soils.
Do you have in the back of your mind a value of, say, SPTs that you run into in soils that would limit the use of DMTs?
That would limit the use of DMTs.
So basically, is there a soil too stiff to get a DMT test to run in?
Yes, there is. I'm sure that has. Normally in the projects that I've seen, at least where we've deployed DMTs, it usually doesn't happen until you get, a practical refusal on some very dense, 50 below material that doesn't allow penetration. But that's probably a really good question for Roger, actually, who is an expert in the field.
For the tooling guys.
Yeah.
I know in my experience, it's really talking to the drillers and seeing what their equipment can handle as well.
Yeah.
It's not always necessarily up to those of us trying to specify them.
Right.
And any of us that have tools, we know there's only certain things you may be willing or not willing to push them through. That's for sure.
Mm-hmm.
And then, as we're talking about all these sort of, once again, advanced tests, when it comes to selling that upfront investment to developers, owners, other engineers, any of these different groups, is there points or things that you would typically use to kind of get that over the finish line?
Yeah, I guess I really like 2 things, right? I like this graphic. I think it kind of visualizes what I would recommend conversationally, I guess. Also, again, Roger's paper on it. It probably, if you read that paper and understand what approach you can consider, I think it really highlights the importance of making sure that you are making this initial data investment, right? The lowest cost solution really is going to come from the lowest uncertainty. I think that's from his paper, right? So I would push that as hard as you can. I would also suggest highlighting to clients that may be resistant to making this initial geotechnical investment with some anecdotes, right? Share with them some stories of cases where projects they really went for the lowest bid and the least amount of information, and just came back and absolutely bit them, right? So I think that's probably pretty powerful, because people are generally receptive to, we like stories. So anecdotes are probably a pretty powerful tool, I think, among other things.
It is true that we do seem to respond to stories better. I think certainly those of us in the field have a lot of stories, and being able to share them, I think, helps everybody with that. It does take one time getting burned in order for people to learn those lessons.
Yeah.
when it comes to the rigid inclusions, analysis for rigid inclusions, obviously those are going to be slightly different than the aggregate piers. What kind of results are you looking for when you're doing those analyses?
Well, we do a couple different things, right? So we start by analyzing them as piles and figuring out what kind of capacity we're going to get from them, right? A structural capacity and a geotechnical capacity. And then we put together a finite element model, right, to sort of figure out how that interaction is going to take place between the rigid inclusion, the load transfer platform, and your footing as a function of settlement, right? And figuring out from that point, okay, well, we've controlled settlement to the design criteria. And then next we have to figure out, okay, well, did that settlement control result in potentially excessive, punching forces into the footing or into your slab, right? Figuring out what your spacing looks like. How do you reduce the stiffness response on that structural element to within limits, right? So we sort of have to perform additional checks and analyses to figure out that we're not going to crack that slab or punch into that footing. So do we need to thicken up the LTP a little bit to maybe we need to get a little more settlement in there and reduce that structural response. So it's kind of a balance, right? You can iterate on it a bit and you're tweaking things and figuring out, okay, I need to maximize my spacing for that capacity that we have available to us based on where we're going to terminate. There's lots of different considerations there. Is the load actually transferring into the RI, right? Are we making sure that soil arching is happening and that the load is making it into the RI, right? So there's things to be mindful about there. For example, if you have very soft soils, there's probably a really good presentations on the subject, right? Because there's ideal soil profiles for rigid inclusion. So you want something like a pretty decent upper crust of soils above into some soft soil stratum that you're trying to pass, and then ideally into some dense material that you can bear into. And the reason for needing that upper crust up there, again, is sort of that load transfer mechanism to take place. If your soft soils are extremely close to where your bottom of footing is, you may not actually be able to install rigid inclusions because that's going to induce too much stress into your footings. And again, all of this kind of gets understood once you start to get into the finite element modeling and figuring out how those stresses are interacting below the foundation.
So do you have a rule of thumb where you might say, listen, I'm automatically going to switch from aggregate piers to RIs or something like an undrained shear strength or an SBTN value, where you sort of make that decision mentally?
Not really. No. Again, I think going back to what I said earlier is that not all soils are created equal, right? In some cases, we've installed, and it's going to be a function of a lot of different components, right? So there is not a great rule of thumb. Probably anything less than 3 blow count material, you should consider that the risk for APs is going to start to rise at that point. But it won't mean that you can't install them, right? I mean, we've had projects where we're supporting a 2 or 3 story townhome building with 2-foot wide footings and 900 PLF loads. That is and you have, let's say, weight of hammer material 15 foot down. That material probably has no idea that that little townhome is being built on top of it, and we're just putting piers there to control the settlement within tolerance and provide the requisite bearing capacity for the soils in that upper feet, 10 feet or so, or 8 feet or so, or whatever. So there's it's the worst answer to give ever, but it is the answer that geotechnical engineers give. So it's going to depend, right? It depends.
Yeah, I know the lawyers always say if I ask the same question to 6 different geotechnical engineers, I get 7 different answers.
That's right.
But
exactly right.
I guess there was one question that came up. Do you have any experience with the jet grouting and maybe a bentonite, sort of cement bentonite piles for ground improvement? Have you guys done any of that? Have you done any of that personally?
I personally have not. I know I'm positive Keller does that, but I have not had experience with that, unfortunately. I think we're pretty specialized here at Keller, so we kind of become experts in a couple of, and we've moved towards this model recently, I believe. So our teams are kind of subject matter experts, and I have not had the opportunity to work with jet grouting yet. No, I hope to at someday though.
Well, that's great. Well, I really appreciate you presenting and answering all of the questions here. I guess just in the last couple minutes here, do you have any closing thoughts on your time doing ground improvement here with Keller?
No, just again, very grateful for the opportunity to do so. Thank you to Geo-Institute and ASCE for this great series, for the opportunity to share my experience with you guys, and to Keller for letting me, represent our pretty cool company. So that's it for me. Thank you.
Well, Juan, thank you. And we've all certainly learned something here today. I'm going to kick it back over to Brad here so he can give us some good words of encouragement as we move on to the next event.
Thanks for a great presentation, Juan. And thanks, Keith, for running the show today. We really appreciate it. Great job. And it looks like we lost Juan already. He's going to plant the flag and declare victory. Thanks for all our viewers, especially those who submitted questions in the chat. We really appreciate that. That's what makes this a fun and vibrant conversation. So we need that from you. Again, you can make your student programs donation by the end of 2025 so that it's tax deductible in this year. It's really easy to do over at the Geo-Institute website. You want to check out the rest of our web conference sessions, you can get to that at the GI website as well. I put a link in the chat for that. We have 5 sessions remaining, including the one that is starting in about 3 minutes. Great variation of technical topics. Go check it out. Get those year-end PDHs. Our next live stream is tomorrow. It's our second web conference, Lunch and Learn. This one comes from Sequent. You can get information on that on our Eventbrite page, as well as all our other upcoming live streams, because we actually have 2 tomorrow. Geo-Congress preview number 2 is tomorrow as well, and you will want to check that out. Next week, GeoStrata Extra with GeoLegendary Poulos, and then we're done for 2025. So only a couple more remaining. We would love to see you in the chat for those presentations. Juan, thanks again. Keith, thanks again. Our producer today was Aurora Flieger, and we will see everybody really soon with another Geo-Institute live stream.